Hi all, today we start discussing our syllabus, section 2, binary operation. This is the first session. We start with the definition of, this is definition 2.1 definition. This is the definition of a binary operation. A binary operation, it is denoted by star on a set S is a function mapping S cross S to S. Okay? So any function from S cross S to S is called a binary operation, and we denote that binary operation with a star. We will denote the element star of AB. Since the star is a function from S cross S to S, each pair A comma B is assigned by an element from S, and that is denoted by this star of AB, and we write that element as A star B. Okay, so if we have S cross S here, this is S cross S, this is S cross S, and this is S. So star is a function from S cross S to S, and if we choose any ordered pair AB, there should exist exactly one element C in this set S. Okay, so this rule is what we call the binary operation. So we denote this C as star of AB. Okay, so this is the image of A comma B under star. Okay, and this situation is denoted by A star B is equal to C. So for the convenience, we write this notation A star B equal to C to denote this star of A comma B is equal to C. For example, we can take the real numbers. Set of all real numbers is denoted by this symbol R. Under addition, okay, set of all real numbers under addition, or you can define addition as a binary operation of R, or you can denote this as pluses from R goes R to R, and it is denoted by plus of A comma B is equal to A plus B. Okay, so this is an example of binary operation, and if we consider set of all matrices set of all matrices with real entries, that is denoted by M of R. Okay, so this is the set of all matrices with elements from R. Okay, so this set consists of a 1 2 3 4 comma, for example, say some 2 3 and we have 5, and we have 5 6 7, etc. These are some of the members of this set, and if we denote plus in this set, plus is that is usual matrix addition, so that is not a here matrix addition plus. This is not a binary operation. Okay, because we cannot add these two elements, because in order to add two matrices, those matrices should be of same orders. So here this M of R, set of all matrices over R, consists of all the matrices of different orders. So if we choose any some pairs from this, say this is A and this is our B, then A comma B, we cannot assign an element for this A plus B. Okay, so matrix this addition is not a binary operation of this collection. Okay, so we have seen this an example of binary operation and non-example of binary operation right now. Another interesting case is if we choose R star. This R star is set of all non-zero real numbers. Set of all non-zero real numbers. that is denoted by R star. When you consider addition on this set, here this addition is not a binary operation, because we choose two elements from this. In fact, this R star can be denoted by R minus set 0, set of all non-zero real numbers. From this you can choose 2 comma minus 2. Okay, what is the image of this pair? Under addition, that is 2 plus minus 2. That will be 0, but this does not belong to R. So this plus cannot be considered as a function from R cross R to R. Okay, that is the reason why we cannot consider this as a binary operation. In the textbook there are several examples are given, so please go through it, and if you have any doubt we can interact in Google Meet or any other online mode. So please go through it. Please try to work it out in your notebook. Now we have another definition, of commutativity of a binary operation. Okay, a binary operation, and that is denoted by star. So a binary operation star on a set S. The set should be non-empty anyway. Is commutative if and only if and only if. This is the definition, that's why we call this if and only if. A star B the same as B star A for all A comma B belongs to S. That means if you assign an element to this A star B, the same element should be assigned for this B star A. Okay, that means a B comma A. So that is the meaning of this commutativity. So this will be true for every A comma B belongs to S. For example, if we consider R under, or we write it as set of all real numbers addition. We have considered addition on set of all real numbers is commutative, because if you have any A plus B, that is same as B plus A in R in real numbers. So this is an example. This is true for every A comma B belongs to R. Now for non-example, we consider set of all matrices of order n. Okay, that is denoted by this. Please note these symbols. We will later use these symbols. MNR is set of all A belongs to M of R. M of R is set of all matrices whose entries come from that real numbers, and this is the special type of matrices whose order is n. Okay, A is a square matrix of order n. So this is the set consisting of n by n square matrices, and it is denoted by M and R. If we consider this M and R and if we define multiplication, this is usual matrix multiplication. This is not a commutative binary operation. In fact, it is a binary operation, but it is not commutative, because if you have any product of any n by n matrices, any two n by n matrices, that will give another n by n matrix as well. So this is always a binary operation, but it is not commutative. But because we know that A times B, A into B need not equal to B into A for all. Okay, so this never happened for all A comma B. Then we can consider this as a binary operation, which is binary operation on M and R this usual matrix multiplication is a binary operation on MNR, but it is not commutative binary operation. So next is another definition, associative binary operation. A binary operation on a set S is associative if A star B star C equal to A star B star C. Okay, so if this happens for every A, B, C, A, comma, B, comma, C belongs to S, then we call this this binary operation as is an associative binary operation. So for example is trivial, that is real numbers under real numbers with addition is a associative binary operation because we know that this is associative is an associative binary operation because we know that A plus B plus C is same as A plus B plus C for all A comma B comma C belongs to R. Okay, but at the same time, if we have a set of all real numbers with subtraction, if you consider subtraction, is a binary operation, on R, because if you have any this is because of so we have A minus B belongs to R for all A comma B. Okay, so this is a binary operation, but it is not associative. It is not associative. It is not associative because you know that 1 minus 2 minus 3, the value is this is minus 1 minus 3, that is minus 4, but which is not equal to 1 minus 2 minus 3. This is in fact this is 1 minus of minus 1, that is 2. So this is 2, which is equal to this 1 minus of 2 minus 3. So these two for these three triplet we have A plus B plus C is not equal to A plus B plus C. So A minus B minus C using negative sign and using subtraction. So this is a non-example for non-associative or associative binary operation, non-example for associativity. So we can consider this as example and this as non-example. Nevertheless, these are all binary operations on this set R, real numbers. Next we will prove a theorem 2.13. So this proves the associativity of composition of two functions. That means if you have a set and if you consider set of all f from f is a function, set of all f from S to S. Okay, set of all function from S to S. So this is our capital S is a set, and consider set of all functions. Okay, this f is a function from S to S. Okay. Now, if we choose any, this is another set. We call this as some capital A. We can denote this as some capital A. So, if we choose any three elements f, comma g, comma h belongs to A, then we can say that f composition g of x, it is defined as f of g of x. So, this is again a function. Okay. If we denote this by some f1, then f1 is a function from again S to S. Okay. Now, if we consider this set A with in A, this composition is a binary operation. Okay. Now you can verify the associativity of this composition that is F composition G composition H. What is F composition G composition H? In fact, this is a function from S to S, so it is also a member of capital A. Then how will you evaluate this F composition G composition H of X? That is F composition G composition H of X. Okay, so that is nothing but G of H of X. And what is F composition this quantity? So that will be F of G of H of X. Okay, so similarly you can evaluate F composition G composition H of X. So this will be F composition G of H of X. Okay, so this is nothing but F of G of H of X. So from these two statements we can get F composition G composition H is same as F composition G composition H. Okay, so this is the associativity of this composition. Okay, now you can consider this composition is as a remark. You can note this composition is a binary operation on this capital A. Okay, so we know that, but this is not the commutative binary operation. You can easily prove that F composition G need not be equal to G composition always. So there are some sets in which this composition is not a commutative binary operation, but it is associative binary operation as well.